All right, well, here comes our next video presentation. You might have been asking yourself, what's twice as much fun as one-dimensional motion? Well, two-dimensional motion is one of the possible answers to that question. All right, well, we'll see what we got here with two-dimensional motion. As usual, I'll present here the basics, and you should be already thinking as you hear them, where could I take this? What could the applications be? And what more complicated type of problems could I face? Because these are the introductory ones. All right, so we'll get started with that in mind. There's a pretty good example there, two-dimensional motion. Probably more three-dimensional motion with the snowboarder flying through the air, but we'll limit ourselves here to two-dimensional motion. We'll make some other simplifying assumptions as we go along, and the introduction will include a particular type of two-dimensional motion, and that's projectile motion. So projectiles are anything that are flying through the air where just gravity are affecting them. Already we're making a simplifying assumption because objects flying through the air have things besides gravity acting on them, for example air resistance. In most of our problems we'll rule out the air resistance, but certainly that would be one of the things that you should be thinking about of where we could take this topic, because air resistance is real. Okay, so give examples of some projectiles. If you want to even just think about a couple of them here, that would be, I guess, a good way of thinking where this topic could go. And also, how has this study been important for human beings? So that's something I'd like you to think about anyway. All right, let's get into it here. Projectile motion has two components. Now, we've already worked with vectors and splitting vectors into their components. And we'll stick with the idea of talking about a horizontal and a vertical component. Here is a person being shot out of a cannon, and I think we've all been there at one time or another, shot out of a cannon. But in this idea of ruling out three dimensions of motion, you would observe that a person flying through the air launched from a cannon would be traveling horizontally and at the same time vertically. So there's a projectile. It's flying through the air. And if it's two-dimensional projectile motion, it's going to have components in the horizontal and vertical direction, at least. All right, so a little bit of vocabulary. The path that a projectile is going to take is the trajectory, and how far it lands away horizontally is the range. Why would we care about the range of a projectile? It's another interesting question to be asking. Okay, well, if it was cannons, as this picture suggests, you would care if you were being fired upon, whether you were in range or not. And of course that opens up a whole line of thinking there with projectiles and range. Okay, so we will start as easily as we can and build it up from there. So a particular type of projectile is going to be a horizontally launched projectile. So maybe something that is shot horizontally, and if it's going to be two dimensions, obviously it's going to be shot from a height. So it will be shot from a height and will have a range in the horizontal direction. So there would be, we could see a horizontal range, let's say. That's why x is equal to r in that picture, and a vertical height, where h is representing height in the y direction. Okay, so there's a machine that does it, and we'll work with some launchers in class that are going to be similar to this in design anyway. Okay, so here's some things that we could always say to get started. Well, one thing I can say before I get started is all the equations that we've developed in one-dimensional motion are still good. You can only use them, however, in one dimension, meaning that you have to separate the horizontal components with the vertical components. Once you've separated them into horizontal, in the horizontal direction, you can use the equations that you become accustomed to. And in the vertical direction, also, you can use the equations that you become accustomed to. All right, so we are going to make a simplifying assumption here that in the horizontal direction there is no wind resistance. So we will say the acceleration is equal to 0. And because of that, we will say that the v, at least in the horizontal direction, is going to be constant. And that means that the distance that it travels horizontally, the range, will be that speed multiplied by the time that it travels horizontally. In the vertical or the y direction, we could say, since it's in the downward direction, we could say the acceleration was a positive 9.8 meters per second squared. To note here, you could also say it was a negative 9.8 meters per second squared, as long as you kept your vertical displacements negative. That's the arbitrariness of the signs. So whatever your preference is there. Here I say it's positive, but you could use negative just as well. If I'm doing that, I'm going to say, well, regardless, I'm going to say that the initial velocity in the vertical direction is 0. The projectile was fired horizontally, so it had no velocity in the vertical direction to start with. That changes because of gravity. Okay, so I can also say that the distance, and here I would make my distance or displacement in the vertical direction a positive number, just like my acceleration. Once again, to note, if I wanted to make the acceleration negative, some people like downward to always be negative, then that would be okay as long as I made my displacement negative as well. I've noted here also that the displacement in the vertical direction will be 4.9 t squared. And that'll always be true since the initial velocity is 0. Can you derive that for yourself? It's a pretty straightforward derivation, but nice to convince yourself of it, I suppose. Okay, so what else can we say here in the horizontal direction? The overall velocity is going to be the combination of the velocity in the x direction and the velocity in the y direction. And we'll be able to use some right angle trigonometry on that as well to figure out what's going on because they're always at 90 degrees angles to each other. And if you picture them as a head-to-tail diagram, you're really ready to go with that Pythagorean theorem. Notice here that they're indicating v in the x or v in the x naught. That's similar to what your formula sheet does, indicating that it's one direction at a time, either the x direction or the y direction. Okay, so here the initial velocity is all in the horizontal direction. The initial velocity in the y direction is 0. Okay, and it does become a combination of both the x and the y, so that's something to bear in mind. Okay, here's an example for you. Let's see if you've got it. Separate it into horizontal and vertical components. See if you can answer these questions. And if you do, I guess already ahead of time I'm giving the answer here. But yeah, give them a shot. See if you can figure out the range of the soccer ball and then the height of the cliff. Pause and come back to us when you're ready. Okay, hopefully that worked out. And if it did not work out, then maybe you can ask about it in class. See how that's going to be solved. Okay, you might be asking yourself, why is somebody kicking a soccer ball off a cliff? Well, I don't know. But at any rate, just important to notice that the x and y components are just acting independently, so they are separated from each other. And here's a classic question. That if a bullet is fired horizontally and another is dropped at the same time from the same height, which bullet is going to hit the ground first? So maybe you pause and think about it, and we'll come back with the answer. All right. The answer, which I see maybe cut off here, is that neither one of them do. They hit the ground at the same time. What's going on horizontally does not affect the vertically, so vertically it's the same thing whether you drop it or fire it. Of course, there is air resistance to consider, but that's an interesting one there. In a vacuum, that should happen. A vacuum without air resistance. Okay, another interesting case here is a projectile that's fired at an angle, where the landing height is equal to the launching height. Again, we'll take these examples that we're presenting here, and then we'll try to apply them to more complicated situations down the road. And you should already be thinking in those terms. What other ways could you fire a projectile that might show up in a problem? Okay, at any rate, a question to be asking yourself is, here's a projectile. Once the motorcycle gets in the air, it's a projectile. What are the factors that affect the height and the range of the motorcycle? So be thinking about that. Hey, and if you remind me, I'll tell you a motorcycle story in class. You got to follow your laws of physics, but yeah, you have to remind me to tell you that story. Okay, so let's see. How about this as a basic question? Which angle gives the farthest range out of all the angles? Well, turns out a 45-degree angle will. Somewhere in the middle will give you a range that, is the farthest. Higher angle, it's going to go higher, but it's not going to go as far. And a lower angle gives you low height and range, which probably makes some sense. Okay, so a little trigonometry review that we've done before. We've got the idea of the three sides of a triangle, the hypotenuse being the side opposite the right angle. I should say we've talked about right triangles, and this is true for those. And here are some of the definitions, the SOHCAHTOA, if you will. So, if you were to find the sine of 30 degrees, you would take your calculator and it would tell you, and that would mean also that the opposite over the hypotenuse would give you the sine of 30 degrees. And the flip around of that is, which I see is also cut off here a little, are the inverse functions. With the inverse functions, you can backtrack and find out what the angle is. Always a good idea, as I've mentioned before, to make sure that your calculators are in the degree mode, or else everything gets thrown off. Okay, so let's see here. We've already gone through the Pythagorean theorem, so we know this part of it. And here's a picture that's showing you again the initial velocities. For a problem like this, or a diagram, a vector diagram of the initial velocity of a projectile fired and landing at about the same height. So horizontally and vertically, you're going to split up the components. Using that trigonometry and that terminology with the x there that's similar to on your formula sheets, we can find out the horizontal speed and the vertical speed. And that means if we're making the simplifying assumption that the acceleration is 0 in the horizontal direction, and now I'm going to call my upward velocities in the vertical direction positive, and here I will call the acceleration negative to show that it's working against that velocity. It's slowing it down. And then I would say that the velocity in the y direction is 0 meters per second when it gets to its highest point, halfway through the trip. And that means that I can say that the time in the y direction is that initial velocity in the y direction divided by 9.8. Another one that I challenge you to see if you can derive. It's a pretty straightforward derivation anyway, given the information in front of you. Okay, so that's the time to the highest point, and that time to the highest point is half of the trip. So the time in the horizontal direction is going to be double that time. That's, of course, assuming that they are launched and landing at the same height. Okay, and that means also that we could say, with the simplifying assumption that there's no air resistance, that the range is going to be that velocity in the y direction multiplied by the time in the y direction. Okay, here's a sample problem for you. Why don't you pause and see if you can find it, the answer to what is its range, and also how high does it go. That doesn't show up on the screen, but try to find how high it goes as well. All right, and let's take a little bit of a pause right there. Okay, so as we resume that here. Yeah, so again, here is the question, what is the range, and also how high does it go? If you pause, we can get back in a minute, and when you're back, the answer should be 883 meters of range and 128 meters of height. Okay, so let's see here. How about this one? We'll pause and we'll give this one a try to answer what was its initial velocity. And with a spoiler alert, I'll have the answer when we get back, which is, all right. So here's one more you can try, and we'll pause, and we're back, and there you go. All right, here's one for you too, a question to leave you with, so maybe pause. I'll leave you to think about this one, and that is about it for this presentation. Look forward to seeing you in class.